So hello again to all the viewers. Here we are looking at part C of this problem. If you haven't looked at part A and part B, I recommend you to go to my first video on this problem. I will put the link in the description. So in the C part, we have to transform our ellipsoid into a needle. So now in part B, we transformed the ellipsoid into a two-dimensional object. In part A also, in both A and B, we transformed the object, the given ellipsoid into a two-dimensional object. First a disk and then an infinite ribbon of length infinity. In this part, we have to transform it into a one-dimensional object, which is a needle. So now two of the parameters have to go to 0. So because our needle spans from x equal to minus a to x equal to plus a, so the needle still has an x dimension, but it does not have the y and z dimensions anymore. So the parameters b and c must go to 0 now. So that is the transformation that we have to make, and because they both go to 0, at the outset I assume that b and c are equal. So as I make, even before I make b and c approach 0, I make them equal. So I assume that our we are beginning with an ellipsoid in which the quantities b and c are equal. You will see that this makes the problem very easy to think about. So b and c are equal, and therefore we start with this formula sigma. So the question says that we ultimately have to find the charge per unit length on the conducting needle. So we have a needle from minus a to a. It's just a line, like in electrostatics we encounter line charges. Where charge is distributed along a line, it has a particular charge per unit length. Here the charge per unit length might be varying. You would expect that it will vary from x equal to minus a to x equal to a. So we have to find this dependence lambda on the dependence of this lambda on x. So we begin with the given formula for the surface charge density, and I put b equal to c first. Then I use the ellipsoid equation to eliminate y and z both at one go, because of course this object of ours does not have the y and z dimensions anymore. So I know at the outset that whatever I am trying to find, which is the charge per unit length, is not going to depend on y and z. The y and z will not even appear in the formula, because the object that we are going to have will not have this y and z dimensions at all. So I eliminate y and z. This is my hint, this is my beginning, this is a clue as to how to begin towards the solution. So y and z are eliminated and we get this. So now in this sigma we have to take some kind of limit, but first we have to turn this formula for surface charge density into formula for linear charge density, which is lambda. So we will do that now. So we know that so let us look at this object here. So this is our ellipsoid, and if b and c are becoming smaller and smaller, it is going to look more and more like a needle, going to look more and more thin, so as if it's just a line along the x-axis. So let us assume that we are somewhere in that process. So b and c are in the process of decreasing towards 0. So we are somewhere in that process. So how do you change the surface charge density sigma into the linear charge density lambda is what we are going to look at. So suppose you have two lines perpendicular, or two planes perpendicular to the x-axis. So I have drawn these two lines to represent those two planes. Two planes perpendicular to the x-axis intercept a small part of this object, right? And this object is only a surface. It doesn't have a volume inside it. The volume is not what we are looking at. We are only looking at the surface charge. The charge is distributed along the surface. So if I cut this object by two planes which are a very small distance apart, the planes are perpendicular to the x-axis and they are a very small distance apart. The small strip enclosed within these two planes, right? If the total charge that is contained on them is, let's say, some q, if I divide that charge q by the length intercepted between them, that is going to give me the charge per unit length. That is the meaning of charge per unit length. So what is the meaning? So what is the length here? Which length is being talked about in this case? The length along the x-axis. The length is being measured along the x-axis, right? So if I have a length dx intercepted between the planes and a charge dq is amount of charge on that particular strip which is intercepted between the planes is dq, the charge per unit length will be dq by dx, right? So how do I go from this sigma to this charge per unit length? So suppose that on all these points, so clearly so if I look at this formula that I've achieved here, if you look at this formula, this sigma only depends on x. This sigma only depends on x. So if I get a strip, so if I cut this object by two planes, as I've told you, and I produce a strip which goes all around, you know, it's a circle basically. It's a circular strip, right? Why? Because any section that you cut with a plane perpendicular to the x-axis will produce a circle. You know, you can imagine that. That will take a little bit of imagination, but that's not very difficult because we have made B and C equal. Remember that B and C are equal here, and so it will be a circle. So the circular strip that I produce by cutting it by two planes which are very close together, the surface charge density over all points on that circular strip will be the same because they lie at the same x coordinate. The x coordinate for all the points on that circular strip which is intercepted between the planes, the x coordinate is the same. So the sigma will be the same. So if I multiply that sigma, because sigma is charge per unit area on that strip, but I want the total charge intercepted, total charge on that strip. I want the total charge on that strip. The total charge on that strip will be the charge per unit area times the area of the strip. The area of the strip will be the circumference of the strip times the length dx, right? So the total charge that I produce will be sigma times the circumference times dx. And if I look at the total charge in terms of the charge per unit length, it will be lambda times dx. So I have not written this over here. You can write it on your own. It will make your thinking sharper because as I talk, if you try to follow my words and if you try to write it on your own, it will make you learn better, right? So the charge per unit length lambda times dx is one way of writing the charge on that strip, and sigma times the circumference of that strip times dx is another way of writing charge on that strip. So if we equate the two, we get that charge per unit length is equal to sigma times the circumference. Charge per unit length will be the sigma at that point, and sigma will be the same on all those points because they lie at the same x. And if I just multiply it by the circumference of that strip, the circumference means the circumference of the circle, of the circular strip that we produce. So how do we find that circumference L? How do we find that circumference L? Again, using the ellipsoid equation. So this is still an ellipsoid, and if I cut it with a plane parallel to the perpendicular to the x-axis, I get a circle, and this circle equation, the equation of that circle is achieved from this ellipsoid equation. So if I take x to the other side, so I produce this formula: y square plus z square equal to b square times 1 minus x square by a square. So how is this equation of a circle? So it's a circle in a plane which is parallel to the yz plane. So if I write it like this, if I write the ellipsoid equation like this, then y square plus z square equal to r square. This equation is of the form y square plus z square equal to r square, which is the equation of a circle, and the right hand side is the square of the radius. So as I take different values, various values of x, so if I put x equal to 0 here, the radius of the circle produced is just b, right? That makes sense, because if I measure this distance, so if I measure the distance from the origin to this point on the y-axis, it's b, right? So if I cut this object with the plane with the yz plane, I get a circle of radius b. If I put x equal to, let's say, a by 2, I get b square, 3b square by 4. So the radius there is root 3b by 2. So for different values of x, you produce different circles, and the radius is different, right? So as soon as you put a value of x here, right, in this equation, as soon as you fix the value of x, fixing the value of x in this equation is equivalent to saying that you are cutting the ellipsoid with a plane perpendicular to the x-axis, because on that plane the x coordinate of all the points are the same. So you're just fixing you want only those points of the ellipsoid which have a particular x coordinate, which is the same as saying that you're cutting the ellipsoid with a plane perpendicular to the x-axis. So as soon as you do that and you rewrite the equation like this, you see that it's a circle. So as soon as you cut the ellipsoid with a plane perpendicular to the x-axis, you get a circle with a certain radius which depends on where you cut it. And so if this is the radius, this is the radius squared, by the way, then the circumference of that circle will be 2 pi times the radius. So it will be b 2 pi b times 1 minus x square by square under the square root. So this is the circumference of that circle, and therefore the charge per unit length on the charge per unit length at that point, for that particular point, for that particular value of x, will be found by sigma times L. And of course, if I leave it like this, for example, if I leave it like this and I don't put b going to 0, this is going to be my answer, right? So, suppose I don't put the limit b goes to 0. This and I say this is the charge per unit length. Charge per unit length is q by 2a times this whole thing. This whole expression is my charge per unit length. This will be my answer if I have an ellipsoid whose for which the quantities b and c are equal, and they are both represented by b, and so this will be the charge per unit length at a particular point denoted by the x coordinate x, right? And the charge per unit length is independent of y and z. It is very intuitive that the charge per unit length will be independent of y and z because because of the symmetry, because it's a circle, and the circle has a symmetry. No point on the circle is any different from any other. So as soon as you fix the x coordinate, the charge per unit length, I'm sorry, the charge per unit length does not depend on y and z because it's a total charge that you're measuring. It's not the surface charge density. I'm sorry, it's not the surface charge density. It's the charge per unit length. So it depends only on x, because it's the charge which is intercepted between two planes cutting the body perpendicular to the x-axis. It's the total charge on that circular strip. It's the total charge on that circular strip. So any dependence on y and z will not make any sense at all. It doesn't even make sense any dependence on y and z doesn't even make any sense. So this is the lambda if b is not 0, if b is finite, if b has a particular value. But as we make b going to 0, it turns into a needle. This is still an ellipsoid, but if b becomes extremely small, it becomes a needle. And in that case, this term disappears, this term goes to 0, and then these two terms are reciprocals of each other, and therefore we get that the lambda becomes a constant, which is quite astonishing, given that it's a needle, and you would not expect charge to distribute uniformly over that needle, over a linear object, but it really does. And that's quite surprising. So you can see that when b was some finite value, the object was still an ellipsoid, and in this case the lambda was non-uniform. It is clearly non-uniform. It depends on x. It changes as x changes. So we can draw a graph for this function. We can see where it reaches a maximum, where it reaches a minimum. So I can see, for example, that if I put x equal to a here, this whole term becomes 0, and this makes the whole thing 0, because at x equal to a, this is 0, this is also 0, but this is non-zero. b square x square by a to the power 4 is non-zero for x equal to a, and therefore the whole thing becomes 0. So for this ellipsoid, the lambda close to the point x equal to a goes to a very small value, goes to 0. But if b is very small, and it becomes a needle, the charge density, the charge per unit length becomes a constant, which is absolutely astonishing and really an amazing result. So we have achieved quite an interesting result just by tweaking the values of a and b and c, starting with the ellipsoid formula and choosing appropriate values of a, b and c. We have transformed it into an object, into 3 different kinds of objects, and found their charge distributions, which is very interesting because they are conductors, and so it is a very interesting insight into the properties of conductors, how conductors behave, how a needle-like conductor will behave, and how a conductor which is very long, which is like a strip, will behave. So you can do another example as a supplement. You can try to find the charge per unit area, the surface charge density for an infinitely long cylinder. So it's an open, it's a hollow cylinder, but it's infinitely long, and it has a radius r. So you can also start with the ellipsoid and transform it into that cylinder. Just as a supplement, you can do that. So thanks for watching. I hope that you found it interesting, and of course the best way to do it is to try it on your own and to solve it on your own. And even after you've watched the video, you should not stop thinking about it. And if you have any questions or doubts or anything that you think is wrong in the way that I did it, you should not stop there. You should investigate that. That if you think it's wrong, then maybe there is something there, and you should try to come up with reasons for why you think it's wrong, and so on. So thank you for watching, and hope you enjoy doing your physics.